Good evening and welcome to Dreamy Academy. Tonight we begin a journey not just through the vastness of space or the depths of time, but into the very fabric of existence itself, the intricate, beautiful tapestry that is all of physics. As we begin, I'd love to know where you're watching from, your city, your country, perhaps even what the night sky looks like outside your window. If you enjoy these peaceful explorations of science, please take a moment to like the video and subscribe. It truly helps this little corner of quiet curiosity grow. To those already subscribed, thank you sincerely for being part of this slow and thoughtful adventure. Tonight, let's begin by considering a beautiful paradox, the profound solidity of everything around you, the chair you might be sitting in, the floor beneath your feet, the very hand you could raise before your eyes. All of it feels undeniably substantial, unyielding. Yet the deepest insights of physics reveal a startling truth. Almost everything you perceive as solid is in fact an astonishing amount of empty space. This isn't a trick of perception. It's the fundamental architecture of matter. To truly grasp this, we must learn to stretch the imagination until the familiar becomes profoundly strange and wonderfully new. It's a journey that rewards patient contemplation, for in understanding the hidden mechanisms of the ordinary, we uncover a universe far more elegant and interconnected than we ever dreamed. This quiet revelation, this gentle dismantling of our everyday assumptions, is where the wonder of physics truly begins, a beauty that lulls not through absence of thought, but through the rich, interwoven tapestry of understanding itself. Have you ever considered the surprising truth about how solid everything around you feels? The table, the wall, the very ground beneath you. They resist your touch. They hold their shape with an impressive, unyielding presence. Yet, if we could shrink down, far beyond the limits of human vision, beyond even the most powerful microscopes, we would discover that this apparent solidity is one of the universe's most elegant illusions. Let's begin by considering the atom, the fundamental building block of all matter. For centuries, philosophers and scientists have pondered the smallest indivisible unit of existence. The ancient Greeks called it atomos, meaning uncuttable. And while we now know that atoms can be cut, or rather split, and are themselves composed of even smaller particles, the atom remains the conceptual cornerstone of our understanding of matter. Imagine, if you will, the simplest atom, hydrogen. It consists of a single proton at its heart and a single electron dancing somewhere around it. A proton is incredibly tiny, roughly 100,000 times smaller than the atom itself. If the nucleus of an atom were the size of a single pea placed at the center of a vast football stadium, the electrons would be like tiny specks of dust swirling somewhere in the outermost reaches of the stadium, and the rest, almost all of it, would be utterly empty space. This isn't just a little bit of emptiness. It's a profound, almost unimaginable void. The atom, which makes up everything, is almost entirely nothing. This picture, while a useful analogy, is still perhaps too concrete. The electron doesn't truly orbit the nucleus in the way a planet orbits a star. That classical image, though intuitive, breaks down at these minuscule scales. Instead, the electron exists in what we call a quote 2. Imagine a fuzzy sphere around the nucleus, a region where the electron is most likely to be found at any given moment, but without a fixed path. It's a diffuse, energetic presence, not a tiny ball following a clear trajectory. This fundamental strangeness, this departure from the clockwork precision we expect, is our first gentle introduction to the realm of quantum mechanics, where reality at its smallest scales operates by rules that defy our everyday intuition. So, if atoms are mostly empty space, and electrons are more like a fuzzy probability than a solid particle, why do things feel so utterly solid? Why can't your hand simply pass through the table? The answer lies not in solidity but in force. The electrons, those diffuse probability clouds, carry a negative electric charge, and like charges repel. When you try to push your hand through a table, the electron clouds of the atoms in your hand come incredibly close to the electron clouds of the atoms in the table. These clouds, though mostly empty, exert a powerful electromagnetic repulsion on each other. It's this mutual push, this invisible barrier of force that creates the sensation of solidity. It's not that your hand is hitting something, quote, 3 in the classical sense. It's that the electromagnetic fields of your atoms are pushing against the electromagnetic fields of the table's atoms. The force is so strong, so pervasive, that it effectively defines the boundaries of all matter. This electromagnetic force is one of the 4 fundamental forces of the universe, and it governs almost every interaction we experience in our daily lives. Light, electricity, magnetism, and the very structure of atoms and molecules. It's the force that holds atoms together, binding electrons to nuclei. But what about the nucleus itself? Inside that pea-sized core in our stadium analogy, there are protons, which are positively charged, and neutrons, which have no charge. How do those positively charged protons, which should repel each other fiercely, stay packed so tightly together? Here, another fundamental force enters the stage, the strong nuclear force. This force is incredibly powerful, far stronger than the electromagnetic repulsion, but it acts only over incredibly short distances within the nucleus itself. It's the cosmic glue that holds the universe's building blocks together, overcoming the inherent repulsion of like charges with a grip that is both immense and exquisitely localized. What this tells us is that the world around us, and indeed our very selves, are not made of tiny, hard marbles packed together. Instead, we are vast, intricate arrangements of mostly empty space, held in shape and given apparent solidity by the interplay of fundamental forces. The beauty of this revelation is that it transforms the mundane into the miraculous. The chair you sit on, the air you breathe, the blood flowing through your veins, all are shimmering fields of probability and force, organized into patterns that emerge into the richness and complexity of our world. There's a particular comfort in understanding that the universe, at its most fundamental level, operates with such elegant simplicity in its rules, even if those rules lead to such profound and counterintuitive outcomes. This understanding that the universe is woven from a fabric of emptiness and force leads us to a fascinating question. If the very matter that comprises everything is so insubstantial, so diffuse, what then of the forces themselves? What is this electromagnetic push, this strong nuclear grip, this invisible hand that shapes reality? And what other forces might be at play, quietly sculpting the cosmos on scales both grand and infinitesimally small? How do these fundamental interactions give rise to the complexity we observe, from the simplest chemical reaction to the intricate dance of galaxies? These are the questions that gently beckon us forward, into the deeper currents of physics as we continue our quiet exploration of the universe's underlying truths. Our journey into the quiet emptiness of everything left us with profound questions, didn't it? We saw how the universe, and indeed our very selves, are intricate arrangements of mostly void, held together and given form by invisible hands, the fundamental forces. We touched upon the powerful electromagnetic repulsion that makes objects feel solid, and the strong nuclear force that binds the heart of atoms. But what is the true nature of these forces, we wondered? Are there other silent architects at play? And how do their subtle dance steps choreograph the grand ballet of the cosmos, from the smallest chemical reaction to the sprawling majesty of galaxies? Today, in our Dreamy Academy, we embark on a deeper exploration of these cosmic orchestrators. We begin to understand not just what they do, but how they do it, peeling back another layer of reality to reveal the elegant mechanisms that govern existence. Imagine, if you will, the universe as a vast, intricate tapestry. In Chapter 1, we marveled at its threads, the atoms and their spacious architecture. Now we turn our attention to the very act of weaving, the forces that pull, push, and bind these threads into the coherent, breathtaking patterns we observe. Let's revisit the electromagnetic force, the one responsible for the seemingly solid chair you might be sitting in, the light that illuminates your screen, and the very chemistry of life itself. We know it governs the attraction between opposite charges and the repulsion between like charges. But how, you might ask, do these forces actually work? Is it simply an invisible rope pulling and pushing? Here, physics introduces a concept both counterintuitive and exquisitely beautiful. Forces, at their most fundamental level, are mediated by the exchange of particles. Think of it like two ice skaters on a perfectly smooth rink. If one skater throws a ball to the other, both skaters will recoil due to the conservation of momentum. It's not a direct push or pull, but an interaction mediated by the ball. In the quantum realm, forces operate similarly. For the electromagnetic force, the Chaston quote Berson, being exchanged is a session photon. Yes, the same fundamental particle of light we perceive with our eyes. These photons, massless and travelling at the speed of light, are the messengers of the electromagnetic interaction. When two electrons repel each other, they are, in essence, constantly exchanging photons, pushing each other away. When a proton and an electron attract, they are also exchanging photons, pulling each other together. This exchange of photons is happening all the time, billions upon billions of times per second, between the electron clouds of your hand and the surface of your desk, creating that sensation of solidity. It's a continuous dynamic interaction, a silent conversation of light particles dictating the boundaries of matter. This is why the electromagnetic force has an infinite range, just like light itself. Though its strength diminishes with distance, its influence theoretically stretches across the entire universe, shaping everything from the molecular structure of water to the intricate dance of electrons in a lightning strike. It is the force that allows for chemistry, for biology, for all the complex interactions that build up from the atomic level. Without the photon, without this electromagnetic messenger, the universe as we know it, with its vibrant colours, its electrical currents, its very ability to form stable structures, would simply not exist. Now, let's descend deeper back into the heart of the atom to the nucleus, where the protons, those positively charged particles, huddle together despite their natural electromagnetic repulsion. What incredible power, we asked, holds them in such a tight embrace? This is the domain of the strong nuclear force, aptly named for its immense power. If the electromagnetic force is a powerful magnet, the strong nuclear force is a cosmic superglue, overwhelmingly potent but with a remarkably short reach. Its messengers are particles called gluons. Imagine these gluons as tiny, energetic threads constantly being exchanged between the quarks that make up protons and neutrons, and also between the protons and neutrons themselves within the nucleus. Unlike photons, which are neutral, gluons carry a property called quote 5, not related to visible colour but a quantum property, and they interact with each other. This unique characteristic means that the strong force doesn't weaken with distance like electromagnetism. Instead, it increases in strength as quarks try to pull apart like a cosmic rubber band. Try to separate two quarks, and the force becomes so strong it's easier to create new quark-antiquark pairs out of the vacuum of space than to break them apart. This is why we never observe free quarks in isolation. They are always confined within protons and neutrons. This incredible strength, mediated by gluons, is what gives matter its mass stability. It ensures that the nuclei of atoms, from the simplest hydrogen to the heaviest uranium, remain cohesive, providing the stable platforms upon which the electromagnetic force can then build the rest of the atomic structure. Without the strong nuclear force and its gluon messengers, atomic nuclei would instantly fly apart, and the universe would be an undifferentiated soup of elementary particles, utterly devoid of structure or complexity. It is the ultimate binder, the fundamental quote 6 of the material world, operating on scales so tiny they almost defy imagination, yet utterly essential for our existence. We've now explored 2 of the universe's fundamental forces, each with its own messenger particle, its own domain of influence. But there are 2 more, equally crucial, though perhaps less immediately apparent in our daily lives. Let's turn our attention to the weak nuclear force. This force is, in a way, the universe's great transformer. While the strong force binds and the electromagnetic force structures, the weak force changes particles. It is the architect of radioactive decay, the process by which unstable atomic nuclei transmute into different elements. It's the reason why a neutron, left alone outside a nucleus, will eventually decay into a proton, an electron, and an antineutrino. This process, known as beta decay, is a direct manifestation of the weak force at work. Its messengers are the W and Z bosons. Unlike photons and gluons, these bosons are massive, which is why the weak force has an incredibly short range, even shorter than the strong force. Imagine throwing a very heavy ball. It won't travel as far as a light one. This mass also makes the weak force, well, weak compared to the strong and electromagnetic forces, though still far stronger than gravity. The W and Z bosons are the universe's tiny alchemists, mediating interactions that change the flavour of quarks and leptons like electrons and neutrinos, transforming one type of particle into another. Why is this important? The weak force is absolutely vital for the life of stars, including our own sun. The fusion processes that power stars, generating the light and heat that sustain life. rely on the weak force to convert protons into neutrons, a necessary step in the chain reactions that produce helium and heavier elements. Without the weak force, stars wouldn't shine, and the rich diversity of elements that make up planets, oceans, and living beings would simply not exist. It's a subtle but profound force, quietly shaping the cosmic furnace and forging the very building blocks of complexity. Finally, we arrive at the most familiar, yet in some ways the most enigmatic of all the fundamental forces: gravity. From the apple falling from a tree to the majestic spiral of galaxies, gravity dictates the large-scale structure of the cosmos. It is the universe's grand sculptor, pulling matter together, forming stars, planets, and black holes, and orchestrating the dance of galactic clusters. Unlike the other forces we've discussed, gravity is universally attractive. It never repels. And like the electromagnetic force, it has an infinite range, its influence stretching across the entire observable universe. Yet, at the quantum level, it is astonishingly weak. So weak that the electromagnetic repulsion between two electrons utterly dwarfs the gravitational attraction between them. If you hold a small magnet to a paperclip, the tiny magnet's electromagnetic force easily overcomes the gravitational pull of the entire Earth. This vast disparity in strength is one of the universe's great puzzles. While the other three forces are well described by the standard model of particle physics, with their specific messenger particles, gravity presents a unique challenge. In the quantum field theory framework, gravity is hypothesized to be mediated by a massless particle called the graviton. However, unlike the photon, gluon, and W/Z bosons, the graviton has never been directly observed, nor has gravity been successfully integrated into a comprehensive quantum theory alongside the other forces. This remains one of the holy grails of modern physics, a unified theory of quantum gravity. Despite its quantum mystery, the macroscopic effects of gravity are undeniable and awe-inspiring. It is the force that gives weight to our bodies, holds the moon in orbit around Earth, and binds billions of stars into magnificent galaxies. It is the force that dictated the formation of the universe from the earliest moments of the Big Bang, pulling together the first clumps of matter, igniting the first stars, and shaping the cosmic web we see today. Gravity, in its quiet, persistent way, is the ultimate cosmic architect, ensuring that matter, despite its inherent emptiness, coalesces into the grand structures that populate the cosmos. So, there we have them, the four fundamental forces of the universe. The strong nuclear force mediated by gluons, the cosmic superglue holding quarks together and nuclei intact, the electromagnetic force mediated by photons, the architect of atoms, chemistry, light, and all everyday interactions, the weak nuclear force mediated by W and Z bosons, the alchemist of stellar fusion and radioactive decay, and gravity, hypothesized to be mediated by gravitons, the grand sculptor of the cosmos, shaping planets, stars, and galaxies. Each force possesses a unique strength, range, and set of rules, yet they all work in concert, a sublime symphony of interactions. Can you imagine the universe without any one of them? Without the strong force, no nuclei. Without the electromagnetic force, no atoms, no chemistry, no light. Without the weak force, no stellar energy, no heavier elements. Without gravity, no stars, no planets, no galaxies, just a diffuse, formless expanse. These forces are not just abstract concepts. They are the very fabric of reality, the invisible hands that shape everything we see and experience, from the fleeting existence of a subatomic particle to the eternal dance of the nebulae. It is their interplay that gives rise to the breathtaking complexity and beauty of the universe. They are the answers to our questions about the how behind the universe's structure, and they open up new vistas for our contemplation. As we conclude this chapter, I invite you to pause and consider this profound revelation. The world around you, the light filtering through your window, the warmth of your skin, the beating of your heart, all are intricate manifestations of these four fundamental forces engaged in an eternal, elegant dance. We have begun to understand the nature of the cosmic weavers, the particles they exchange, and the domains they govern. But what happens when we push the boundaries of these forces? What happens when we explore the very edge of space and time, or delve into the quantum foam where these rules might bend? Our next steps will lead us down even more wondrous paths into the very geometry of the universe itself. Stay curious, my friends, for the journey has just truly begun. And so, we stand at the precipice of a profound realization. Having glimpsed the universe woven by these four fundamental forces, we've seen the electromagnetic force illuminate our world and bind our very atoms, the strong nuclear force forge the heart of matter, and the weak nuclear force sculpt the elements in the fiery crucibles of stars. But gravity, that most familiar yet most enigmatic of forces, lingers like a whisper at the edge of our understanding, its hypothesized messenger, the graviton, still eluding our direct gaze. It is a force that shapes galaxies and dictates the dance of planets, yet at the quantum scale, it is so infinitesimally weak that it vanishes into the background hum of the other forces. This paradox, this vast chasm between the cosmic grandeur of gravity and its quantum elusiveness, brings us to the very heart of modern physics' greatest quest. It is here, at the crossroads of the incredibly large and the infinitesimally small, that we encounter two monumental frameworks, two pillars of thought that have each, in their own right, revolutionized our understanding of reality. We speak, of course, of relativity and quantum mechanics. Imagine for a moment that the universe is a grand, intricate musical composition. The four forces we've explored are like the distinct instrumental sections: strings, brass, woodwinds, percussion, each playing its part. Now, relativity and quantum mechanics are like two different, incredibly successful theories of musical harmony and rhythm. One explains the sweeping crescendos and the majestic architecture of the symphony, while the other deciphers the individual vibrations of each string, the precise breath in each horn. Both are true, both are beautiful, but their languages, their fundamental assumptions about the nature of sound itself, seem to be at odds. Let us begin with the sweeping crescendos, with the universe on its grandest scales, where gravity reigns supreme. This is the domain of relativity, primarily the brainchild of a brilliant mind named Albert Einstein. Before Einstein, we understood space and time as absolute unchanging backdrops against which events unfolded. A second was always a second, a meter always a meter, no matter who was measuring it, or how fast they were moving. Newton's elegant laws of motion and gravity worked beautifully within this framework, explaining everything from falling apples to orbiting planets. But then, the universe began to whisper secrets that challenged this comfortable view. Experiments revealed that the speed of light in a vacuum was always constant, an unwavering cosmic speed limit, regardless of the observer's motion. This seemingly simple fact shattered the Newtonian edifice and led Einstein in 1905 to his special theory of relativity. What does quote 9 mean here? It means it applies to observers moving at constant velocities relative to one another, and its implications, they are breathtaking. Special relativity tells us that space and time are not separate, absolute entities, but are interwoven into a single fabric called space-time. And crucially, this fabric is relative. Consider this. If you were to travel at speeds approaching that of light, time itself would appear to slow down for you relative to someone stationary on Earth. We call this time dilation. Your clock would tick slower, your heartbeat would slow, your aging process would decelerate, and simultaneously, distances along your direction of travel would appear to contract, becoming shorter. This is length contraction. It's not an illusion, it's a fundamental consequence of the constancy of light speed. Your perception of reality, your very experience of time and space, would literally be different from someone else's. And then there's the most famous equation in all of physics. E equals mc squared. Energy equals mass times the speed of light squared. This simple formula reveals a profound truth. Mass and energy are not separate entities but different manifestations of the same thing. A tiny amount of mass can be converted into an enormous amount of energy, and vice versa. It's why the sun shines, why nuclear power works, and why those minuscule W and Z bosons of the weak force are so massive. They are in a sense condensed energy, but special relativity, as revolutionary as it was, didn't account for acceleration, or more importantly gravity. That came in 1915 with Einstein's masterpiece, the general theory of relativity. This is where the universe truly began to stretch our imaginations. General relativity didn't just change our understanding of gravity, it redefined it. Newton saw gravity as a mysterious force pulling objects together. Einstein, however, proposed something far more elegant. Gravity is not a force, but a manifestation of the curvature of space-time itself. Imagine a bowling ball placed on a stretched rubber sheet. The heavy ball creates a dip, a curvature in the sheet. Now, if you roll a marble across that sheet, it won't travel in a straight line. It will curve inward towards the bowling ball, not because the bowling ball is pulling it, but because the sheet itself has been warped. In the same way, massive objects like planets and stars don't pull on other objects. They warp the fabric of space-time around them. Objects, including light, then follow the shortest path through this curved space-time, and we perceive that path as gravity. This stunning insight explains everything from the precise orbits of planets to the bending of starlight around massive objects, a phenomenon famously observed during a solar eclipse that confirmed Einstein's theory. It predicts the existence of black holes, regions where space-time is so intensely curved that nothing, not even light, can escape. It also predicted gravitational waves, ripples in space-time itself, like waves spreading out from a pebble dropped into a pond caused by violent cosmic events like colliding black holes. These waves, first directly detected in 2015, were a triumphant confirmation of Einstein's genius, a cosmic chorus echoing across the universe. So, General relativity gives us a magnificent, continuous and deterministic picture of the universe on large scales. It describes a cosmos where space-time is a dynamic, malleable entity, where gravity is an elegant geometric consequence, and where events unfold with a predictable, majestic rhythm. But now, let us turn our gaze from the cosmic symphony to the individual vibrations, to the strange, fuzzy, and profoundly counterintuitive world of the infinitesimally small. Welcome to the realm of quantum mechanics. If relativity describes the universe as a smooth, continuous tapestry, quantum mechanics suggests that, at its most fundamental level, reality is more like a pixelated image made of discrete, indivisible packets, quanta. This idea first emerged when physicists tried to understand how light and matter interact at the atomic level, and the classical physics of Newton simply couldn't explain their observations. One of the most mind-bending concepts in quantum mechanics is particle-wave duality. For centuries, light was debated. Was it a wave or a stream of particles? Quantum mechanics answers, quote 11, light behaves like a wave. Think of ocean waves, with crests and troughs, when propagating but interacts with matter as discrete packets of energy called photons, which we met as the messenger particle of the electromagnetic force. Even more astonishingly, matter itself, electrons, protons, atoms, also exhibits wave-like properties. You, the chair you might be sitting in, the very atoms of your body, have a wavelength, albeit an incredibly tiny one, far too small to ever observe in our macroscopic world. This duality means that quantum entities don't have a single, definite location or momentum until they are observed or measured. Before measurement, they exist in a superposition of all possible states, like a ghostly probability cloud. Where is an electron in an atom? It's not at a precise point, but rather spread out in a cloud of probability, a region where it is likely to be found. Only when we try to pinpoint it does it quote 13 into a definite location. This leads us to another cornerstone of quantum mechanics, Heisenberg's uncertainty principle. It's not just that we have clumsy instruments, it's a fundamental feature of the universe. It states that you cannot simultaneously know, with perfect precision, certain pairs of properties of a particle, such as its exact position and its exact momentum. The more precisely you know one, the less precisely you can know the other. It's as if the universe itself has a built-in fuzziness, an inherent limit to what can be known about reality at its deepest level. Determinism, the idea that every event is causally determined by an unbroken chain of prior occurrences, breaks down in the quantum realm. Instead, we deal with probabilities, and this is where the conflict truly emerges. General relativity provides a smooth, elegant, deterministic picture of a universe where everything follows predictable paths through curved space-time. Quantum mechanics, on the other hand, describes a grainy, probabilistic, fundamentally uncertain reality where particles pop in and out of existence, exist in multiple states simultaneously, and where observation itself plays a role in defining reality. They are both extraordinarily successful theories, each verified by countless experiments within their respective domains. Relativity perfectly describes the cosmos, the bending of light, the dance of galaxies. Quantum mechanics perfectly describes the atom, the behavior of electrons, the nature of chemical bonds, and the forces that govern the subatomic world, the strong, weak, and electromagnetic forces, all of which have quantum field theories describing them. But when we try to combine them, when we try to describe gravity at the quantum level, or understand what happens inside a black hole where both extreme mass and extreme smallness converge, their mathematical frameworks clash violently. They speak different languages, making different fundamental assumptions about the nature of space, time, and matter. This, dear friends, is the grand challenge of modern physics: to find a unified theory, a theory of everything, that can reconcile general relativity with quantum mechanics. It is the search for quantum gravity, a quest to understand the universe as a single, harmonious composition, where the sweeping crescendos and the individual vibrations are all part of the same beautiful melody. It is the quest to understand the universe from the largest scales down to the quantum foam, where space-time itself might cease to be smooth and continuous, and instead become a bubbling, frothing sea of quantum uncertainty. What does this mean for our journey? It means we are on the cusp of exploring the very edge of human knowledge, where the known gives way to the unknown, where the most brilliant minds are still grappling with the deepest mysteries. It means stretching our imagination even further as we ponder what kind of theory could possibly bridge this monumental divide. And it means recognizing the incredible beauty and elegance of the universe, even in its unresolved questions, inviting us to patient contemplation of the deepest truths. If you're enjoying this adventure, don't forget to like the video and subscribe to the Dreamy Academy for more explorations into the fabric of reality. We have journeyed through the universe's fundamental forces, peered into the vast emptiness of the atom, and confronted the profound schism between relativity and quantum mechanics. This violent clash, as we termed it, is not merely a theoretical disagreement. It represents the deepest, most perplexing mystery at the heart of physics, a chasm that prevents us from truly understanding the universe as a coherent, unified whole. Imagine, if you will, two magnificent tapestries. One, woven by Einstein, depicts the cosmos on its grandest scale, galaxies swirling, black holes warping the very fabric of existence, the Big Bang a singular monumental genesis. This tapestry is smooth, continuous, and utterly predictable, its threads of space-time stretching infinitely. The other, an equally intricate masterpiece of quantum mechanics, portrays the universe at its most minuscule, buzzing with probabilistic electron clouds, particles winking in and out of existence, a reality inherently uncertain and grainy, like a pointillist painting seen up close. Both are breathtakingly beautiful, undeniably true within their respective domains, yet they employ entirely different artistic techniques, different languages, different understandings of what constitutes reality itself. The problem arises precisely where these two tapestries must meet. Where does the smooth, continuous realm of relativity yield to the grainy, probabilistic world of quantum mechanics? Where does the certainty of celestial mechanics dissolve into the fundamental uncertainty of the subatomic? For most of our everyday experience, this transition is seamless, imperceptible. The chair you might be sitting in behaves according to classical physics. Its atoms, though quantum entities, collectively create a macroscopic reality that feels solid and predictable. But what happens at the extremes? What happens at the very beginning of the universe, in the unimaginable density of the Big Bang singularity? What happens within the heart of a black hole, where matter is crushed to an infinite density, where space-time itself is so dramatically warped that our conventional notions of space and time break down entirely. At these extreme frontiers, the birth of the cosmos, the ultimate demise of stellar giants, both relativity and quantum mechanics are absolutely essential for a complete description. Yet, they actively contradict each other. Relativity predicts infinite densities and curvatures, singularities where its equations simply cease to make sense. Quantum mechanics, with its inherent fuzziness and statistical nature, suggests that such infinite points cannot truly exist. There must be a quantum limit, a smallest possible unit of space or time, preventing such mathematical infinities from manifesting physically. This is the crux of the matter. We need a theory of quantum gravity, a grand synthesis that can describe gravity not just as the smooth curvature of space-time, but as a force mediated by discrete quanta, much like the electromagnetic strong and weak nuclear forces. If gravity is indeed a force, and if all forces in the quantum realm are mediated by messenger particles, then gravity too should have its own quantum messenger, the graviton. Imagine it, a tiny, massless spin-2 particle, constantly exchanged between objects, subtly tugging and pulling, creating the gravitational attraction we experience. But unlike the photon, which we readily observe as light, or the W and Z bosons, which we detect in particle accelerators, the graviton has never been seen. Why? Because gravity, despite its cosmic reach, is staggeringly weak at the quantum scale. To detect a single graviton would require an instrument of such impossible sensitivity that it makes our most advanced particle detectors look like child's toys. The gravitational pull between two electrons, for instance, is so infinitesimally small compared to their electromagnetic repulsion that it's often ignored in quantum calculations. This extreme weakness is precisely what makes gravity so hard to quantize, to fit into the quantum framework alongside its three more assertive cousins. So, if space-time isn't a smooth, continuous fabric at the smallest scales, what is it? Quantum gravity theory suggests that, at the incredibly tiny Planck scale, an unimaginably small length, about 10 to the negative 35th meters, and an equally minuscule Planck time, space-time itself might cease to be smooth and instead become a frothing, chaotic. Imagine the surface of a seemingly calm ocean. From a distance, it appears flat and continuous, but as you zoom in, closer and closer, you begin to see ripples, then waves, then individual water molecules jostling and churning. At the Planck scale, space-time itself might be boiling with quantum fluctuations, a turbulent sea of tiny ephemeral wormholes and fluctuating geometries, where the very concepts of quote 16 and quote 17, quote 18 and quote 19 become blurred and uncertain. This is a universe far removed from Einstein's elegant, predictable continuum. The search for quantum gravity is not just about reconciling two theories. It's about finding the ultimate blueprint of reality. It's about understanding the universe from its absolute genesis to its potential ultimate fate, from the smallest possible unit of existence to the largest cosmic structures. This profound challenge has driven some of the most brilliant minds in physics to explore radical new ideas, to stretch the very boundaries of human imagination, to build bridges between these two seemingly incompatible pillars of understanding. Among the most prominent candidates for a theory of quantum gravity, two stand out, each offering a vastly different, yet equally mind-bending vision of reality. We won't delve into their intricate mathematical frameworks today. That's a journey for another time, perhaps within the deeper halls of the Dreamy Academy. But we can touch upon their core revolutionary ideas, for they represent humanity's boldest attempts to weave those two disparate tapestries into a single, cohesive narrative. One such contender is string theory. Imagine, if you will, that the fundamental constituents of the universe are not point-like particles at all, but incredibly tiny, one-dimensional vibrating. Quote, 20. These strings, far too small to ever directly observe, are like the strings on a cosmic cello. The different ways they vibrate, the different, quote 21, they play, give rise to all the different fundamental particles we observe, electrons, quarks, photons, and crucially, the graviton. In string theory, gravity isn't an add-on. It emerges naturally from the very nature of these vibrating strings. What's more, string theory often requires the existence of extra spatial dimensions, beyond the three we perceive, curled up so tightly that they remain invisible to us, yet profoundly influencing the universe's behavior. Another powerful contender is loop quantum gravity. Instead of continuous space-time, loop quantum gravity proposes that space itself is granular, composed of discrete, indivisible quanta or atoms of space. Think of it like a finely woven fabric. From a distance, it appears continuous. But up close, you see the individual threads, the loops and knots that make up the weave. In loop quantum gravity, space-time isn't a passive arena where events unfold. It's an active, dynamic entity, woven from these fundamental loops, and its geometry is quantized. Time, too, is not continuous but flows in discrete ticks. This theory offers a background-independent approach, meaning space-time is not a fixed stage, but emerges from the relationships between these quantum loops, a truly revolutionary concept. Both string theory and loop quantum gravity, and other fascinating approaches, are highly speculative, demanding a radical rethinking of our most basic assumptions about reality. They are not yet experimentally verified, but they represent the cutting edge of theoretical physics, pushing the boundaries of what we conceive as possible. They are born from the profound necessity to reconcile the universe's two most successful, yet contradictory descriptions. What does this ongoing quest tell us about the universe and about ourselves? It tells us that our understanding is always evolving, always deepening. It teaches us humility in the face of such cosmic complexity, and wonder at the elegance that must lie beneath the apparent contradictions. It reminds us that the universe is not obligated to conform to our intuitive understanding, and that stretching our imagination is not just a poetic exercise, but an essential tool for scientific discovery. The journey to a unified theory of quantum gravity is perhaps the greatest intellectual adventure humanity has ever embarked upon. It is a testament to our insatiable curiosity, our relentless pursuit of truth, and our deep-seated desire to understand the very fabric of existence. As we contemplate this profound mystery, we recognize that the universe, in its intricate dance of forces and particles, holds secrets that continue to challenge and inspire us, beckoning us to look deeper, to think differently, and to appreciate the astonishing beauty of its fundamental laws. So, as we pause here, at the precipice of quantum gravity, reflect on this. The universe is a place where certainty dissolves into probability, where smooth curves give way to quantum foam, and where the very stage of existence might be woven from vibrating strings or discrete loops. It is a universe far stranger and far more magnificent than we could ever have imagined. We have journeyed far, haven't we? From the illusion of solidity to the grand, sweeping curvature of space-time, and then down into the frothing, uncertain quantum foam, always seeking the threads that weave the universe's tapestry together. We've peered into the profound chasm between general relativity and quantum mechanics, and considered the ambitious yet still speculative bridges like string theory and loop quantum gravity. These theories, in their elegant complexity, attempt to describe a universe where gravity too dances to the quantum tune, where space-time itself might be a symphony of vibrating strings or a granular network of loops. But before we allow our imaginations to soar further into these realms of pure hypothesis, let us ground ourselves for a moment in what we do know, in the incredibly successful framework that has, for decades, allowed us to predict and understand the fundamental particles and forces that govern everything we observe, save for gravity. This framework, this remarkable achievement of human intellect, is known as the Standard Model of Particle Physics. Imagine, if you will, that we are not just explorers of the cosmos, but cosmic archivists, meticulously cataloguing the universe's most fundamental constituents. The Standard Model is our most complete, most precise inventory to date. It is a triumphant testament to humanity's ability to decipher the universe's deepest secrets, a symphony of mathematical elegance that describes 3 of the 4 fundamental forces, the electromagnetic, the strong and the weak nuclear forces, and all the fundamental particles that experience these forces. It is, in essence, the quote 26 quote and the quote 27 quote of almost everything we touch, see, and are made of. So, let us open this cosmic ledger together, and with patient contemplation examine its entries. At the heart of the Standard Model are 2 main families of fundamental particles, the fermions, which are the building blocks of matter, the very quote 28 of the universe, and the bosons, which are the force carriers, the quote 29 or the quote 30 that mediate interactions between these matter particles. Remember our discussion of messenger particles from chapter 2? Here, they find their precise home and definition within this grand model. Let's begin with the fermions, the matter particles. They are divided into 2 subgroups, quarks and leptons. Quarks are truly peculiar. Unlike electrons, which we believe to be fundamental and indivisible, quarks are never found alone. They are always bound together by the strong nuclear force, forming composite particles like the protons and neutrons that reside in the heart of every atom. There are 6 flavors of quarks, and we arrange them into 3 generations. The first generation, comprising the up quark and the down quark, are the most common and stable. Protons, for instance, are made of 2 up quarks and 1 down quark, UUD, while neutrons are made of 1 up quark and 2 down quarks, UDD. These are the quarks that make up you, the chair you might be sitting in, the air you breathe, and the stars that twinkle in the night sky. They are the bedrock of everyday matter. The second generation consists of the sham quark and the strange quark. These are heavier and less stable than their first generation cousins, typically appearing in high-energy interactions, like those in particle accelerators or in the fleeting moments after the Big Bang. And finally, the third generation, the heaviest and most ephemeral, the top quark and the bottom quark. These are incredibly massive, far more massive than even a gold atom, yet they are still fundamental particles, mere points in space, according to the Standard Model. They decay almost instantaneously into lighter particles. Isn't it fascinating to consider that the universe, in its fundamental design, seems to have these three replicating, quote, 32 of matter, each heavier and less stable than the last. Why 3? Why not 1 or 4 or 100? This remains one of the Standard Model's intriguing mysteries, a question that perhaps a more complete theory of everything might one day answer. Then we have the leptons. The most famous lepton, of course, is the electron, the particle that orbits the nucleus, that dictates chemistry, that flows through our wires as electricity, and that is responsible for the sensation of solidity we discussed in Chapter 1. Like quarks, leptons also come in 3 generations. The first generation includes the Susti electron and its elusive partner, the Susti electron neutrino. Neutrinos are ghostly particles, so weakly interacting that billions of them pass through your body every second, utterly unnoticed. They are almost massless, though we now know they possess a tiny non-zero mass, a discovery that actually extends beyond the original Standard Model formulation, hinting at physics beyond it. The second generation gives us the muon and the muon neutrino. Muons are essentially heavier versions of electrons, living for only a fraction of a second before decaying. And the third generation introduces the even heavier tau and the n-tau neutrino, which are even more short-lived. So to summarize the matter particles, 6 quarks and 6 leptons, 3 charged leptons and 3 neutral neutrinos, each with its corresponding antiparticle. These 12 fundamental fermions and their antimatter counterparts are the ultimate constituents of all known matter in the universe. They are the tiny, vibrating notes that, when combined, create the grand symphony of existence. Now let us turn our attention to the bosons, the force carriers. We've met some of them before. The photon Chua gamma, the massless quantum of light, mediates the electromagnetic force. It's responsible for everything from radio waves to X-rays, for holding atoms together, for all chemical reactions, and for the very light that allows you to read these words. It is the messenger of light and electricity. The gluon. G, of which there are 8 different types, mediates the strong nuclear force. As its name suggests, it glues quarks together to form protons and neutrons, and it also binds these protons and neutrons together within the atomic nucleus. Without gluons, matter as we know it simply wouldn't exist. They are the strongest of the forces, acting over incredibly short distances. The W and Z bosons, W plus, W minus, Z0, mediate the CS weak nuclear force. These are massive particles, which is why the weak force has such a short range. The weak force is responsible for radioactive decay, a process vital for things like carbon dating and the energy generation within stars through nuclear fusion. It's the force that allows one type of quark or lepton to transform into another, a cosmic alchemist. These are the fundamental forces and their carriers as described by the Standard Model. But there's one more crucial particle, one more fundamental field that completes this picture, answering a profound question. How do particles acquire mass? For decades, physicists grappled with this enigma. Some particles, like the photon, are massless. Others, like the electron and the quarks, have mass. Where does this mass come from? It was a puzzle that threatened to unravel the entire elegant structure of the Standard Model. The solution, proposed in the 1960s and finally confirmed with the discovery of a new particle in 2012 at the Large Hadron Collider, lies in the eustatus Higgs field, and its associated particle, the Higgs boson. Imagine the entire universe, every inch of space, permeated by an invisible, omnipresent field, the Higgs field. Think of it like a cosmic molasses or a dense energetic medium. As particles travel through this field, they interact with it. Some particles interact very strongly, experiencing a lot of quote 34 or quote 35 from the Higgs field. This interaction, this resistance, is what we perceive as mass. The stronger the interaction, the more massive the particle. Particles that interact weakly with the Higgs field are less massive, and those that don't interact with it at all, like the photon, remain massless. The Higgs boson is the quantum excitation of this Higgs field, much like a ripple on the surface of water. When enough energy is concentrated in a tiny region, it can excite the Higgs field, manifesting as a Higgs boson. Its discovery was a monumental triumph for the Standard Model, providing the missing piece that explained how the fundamental particles acquire their inertia, their resistance to changes in motion, their mass. It completed the cosmic inventory, offering a profound insight into the very nature of existence. So the Standard Model presents us with this beautiful, intricate tapestry. 12 fundamental matter particles, 4 fundamental force-carrying particles, photons, gluons, W and Z bosons, and the all-pervading Higgs field, whose quantum excitation is the Higgs boson. These are the fundamental actors on the quantum stage, performing the grand play of the universe. And what a play it is! The Standard Model has been incredibly successful, making predictions that have been confirmed with astonishing precision in countless experiments. It is the bedrock of our understanding of particle physics, guiding our exploration of the subatomic world. But, as we have learned, the universe is full of mysteries that invite us to stretch our imaginations further. For all its triumphs, the Standard Model is not a theory of everything. It has significant limitations, gaping holes that hint at a deeper, more encompassing reality. What are these limitations? Firstly, and most glaringly, the Standard Model does not include gravity. The gravitational force, that familiar pull that governs planets and galaxies, remains stubbornly outside its elegant framework. This brings us right back to the grand schism we discussed in Chapter 3 and the quest for quantum gravity from Chapter 4. How do we incorporate gravity, the weakest yet most dominant force on cosmic scales, into this quantum picture? This is the Everest of modern physics. Secondly, the Standard Model does not explain dark matter or dark energy. We know from astronomical observations that visible matter, the stuff made of Standard Model particles, accounts for only about 5% of the universe's total mass energy content. The vast majority, about 27%, is dark matter, an invisible substance that interacts gravitationally but not electromagnetically. Hence, quote, 38. And an even larger portion, about 68%, is dark energy, a mysterious force driving the accelerating expansion of the universe. The Standard Model offers no candidates for these pervasive yet unseen components of our cosmos. they remain profound enigmas, pointing to new particles and forces beyond its current scope. Thirdly, the Standard Model doesn't explain why there are 3 generations of quarks and leptons, nor does it shed light on the precise values of their masses or the strengths of the fundamental forces. These are parameters that must be put in by hand, derived from experimental measurements, rather than predicted from first principles. It feels incomplete, like a magnificent puzzle with many pieces assembled, but with no overarching image on the box, and finally does not unify the forces entirely. While it describes the electromagnetic strong and weak forces, it doesn't show them as different manifestations of a single, more fundamental force, as physicists suspect they might be at extremely high energies, like those present in the very early universe. This concept, known as Grand Unified Theory, GUT, is another step beyond the Standard Model, a stepping stone towards a true theory of everything. So, while the Standard Model is an unparalleled success, a dazzling achievement that maps the known quantum landscape with incredible precision, it also serves as a luminous beacon, highlighting the vast territories of the unknown that still await our exploration. It is a powerful lens through which we view the universe, but it is not the ultimate lens. As we conclude this exploration of the universe's fundamental inventory, take a moment to reflect on the sheer audacity of this endeavour, to break down reality into its smallest, most fundamental components, to understand the forces that govern their dance, and to construct a model that has been experimentally validated with such rigour. It is truly astonishing. Yet the very success of the Standard Model highlights its limitations, inviting us to ask deeper questions, to seek a more complete, more harmonious understanding of the cosmos. What lies beyond this inventory? What new particles, what new forces, what new dimensions might be required to complete the picture, to finally weave gravity into this elegant quantum tapestry? These are the questions that continue to drive us, to push the boundaries of human knowledge, and to embark on ever more profound intellectual adventures. Join us again, won't you? Like the video and subscribe to the Dreamy Academy as we continue our slow and thoughtful journey into the heart of physics, ever closer to understanding the grand design of everything. The universe, in its boundless complexity and elegant simplicity, always has more to reveal, and we, the curious, are always ready to listen. Chapter 5, as we recall, laid out the magnificent edifice that is the Standard Model of particle physics. It is a triumph, an astonishing testament to human ingenuity, meticulously mapping out the fundamental particles of matter and 3 of the 4 fundamental forces that govern their interactions. From the fleeting dance of quarks within a proton to the grand electromagnetic symphonies that sculpt chemistry, the Standard Model offers an incredibly precise and experimentally verified account of our universe at its most microscopic. And yet, as we gently concluded our last session, a profound sense of incompleteness lingered, didn't it? Like a masterfully painted portrait missing a crucial defining stroke, or a complex piece of music with a silent essential movement. The Standard Model, for all its glory, does not include gravity, that pervasive, gentle tug that anchors us to our chairs and binds galaxies across cosmic voids. It offers no explanation for the enigmatic dark matter and dark energy, which together constitute a staggering 95% of the universe's mass energy content. nor does it predict the precise masses of its particles or the exact strengths of its forces. These are parameters we must simply measure and plug in, and it leaves the tantalizing possibility of force unification, where the electromagnetic strong and weak forces might reveal themselves as different manifestations of a single, more fundamental interaction, as yet unfulfilled. So, where do we go from here, you might wonder? If the Standard Model is our current bedrock, what lies beyond its carefully constructed walls? This, my friends, is where our journey truly stretches the imagination, where we venture into the realm of theoretical physics, into the bold, often speculative, yet utterly compelling search for a deeper, more comprehensive understanding of reality. We are now stepping into the realm of grand unified theories, or guts, and ultimately the ultimate ambition, a theory of everything, a TOE. Imagine for a moment, if you will, a vast ancient river. As it flows through different landscapes, it takes on different characters, sometimes a raging torrent, sometimes a gentle stream, sometimes a broad, placid expanse. But it is always the same river, fundamentally. Grand unified theories propose a similar idea for our forces. They suggest that at incredibly high energies far beyond anything we can achieve in our most powerful particle accelerators, energies that might have existed only moments after the Big Bang, the electromagnetic strong and weak forces are not distinct at all. Instead, they are merely different aspects, different, quote, 39, quote, of a single, unified, fundamental force. Think of it like this. You observe ice, liquid water, and steam. They appear very different, don't they? Yet, we know they are all just different phases of the same substance, H2O. Their differences emerging only when temperature and pressure change. Guts propose that as the universe cooled after the Big Bang, this primordial unified force froze out or broke symmetry into the distinct electromagnetic strong and weak forces we observe today. This idea is incredibly elegant, a testament to the physicists' enduring hope for simplicity and underlying unity. If successful, a GUT would explain why the strengths of these three forces, which seem so different at everyday energies, appear to converge at extremely high energies. It would also lead to some fascinating predictions, such as the possibility of proton decay. According to the Standard Model, protons are absolutely stable, but in many guts, protons would eventually decay, albeit over timescales far, far longer than the age of the universe. So long, in fact, that observing such an event would require enormous detectors, monitoring vast quantities of matter. Despite decades of searching, we have yet to witness a single proton decay, which places strong constraints on the specific forms GUTS can take. Another intriguing prediction of some guts is the existence of magnetic monopoles, isolated north or south magnetic poles, something never observed in nature, where magnets always come with both poles. The leap from unifying three forces to unifying all four, including gravity, is the ultimate aspiration, a first theory of everything. This is the holy grail of modern physics, a single, comprehensive theoretical framework that would explain all fundamental physical phenomena, all the particles, all the forces, and perhaps even the very nature of space and time itself. It is the quest to reconcile the smooth, continuous, deterministic universe of general relativity with the grainy, probabilistic, uncertain world of quantum mechanics, to weave them into a single seamless tapestry. One of the most promising, albeit highly speculative, candidates for a toll is string theory, which we briefly touched upon when discussing quantum gravity. Remember, string theory posits that the fundamental constituents of reality are not point-like particles, but rather tiny, one-dimensional vibrating strings, unimaginably small, far smaller than a proton, far smaller than an electron, existing at the Planck length. The different modes of vibration of these strings give rise to all the different particles we observe, much like different notes played on a violin string. Crucially, string theory naturally includes a spin 2 particle that behaves exactly like a graviton, the hypothetical quantum messenger of gravity. This is one of its most compelling features, as it offers a way to quantize gravity without the infinities that plague other attempts. But string theory's ambition extends far beyond just gravity. It proposes to unify all forces and all particles within its framework. The electromagnetic force, the strong force, the weak force, and gravity all emerge from the vibrational patterns of these fundamental strings. This is why string theory is often considered a theory of everything. It suggests a universe far richer and more complex than we perceive, often requiring extra spatial dimensions beyond the 3 we experience, curled up so tightly that they are invisible to us, like a garden hose appearing as a 1D line from afar, but revealing its 2D circumference up close. Within the landscape of theories attempting to go beyond the standard model, a concept called supersymmetry, or SUSY, frequently appears. Supersymmetry proposes a deep and elegant relationship between the 2 fundamental classes of particles, fermions, matter particles like quarks and leptons, and bosons, force carriers like photons and gluons. It suggests that for every known standard model particle, there exists a 42, a 43, with a spin that differs by half a unit. So, an electron, a fermion, would have a selectron, a boson, and a photon, a boson, would have a photino, a fermion. Why is this significant? For one, supersymmetry helps to address the quote, 44 which is the perplexing question of why the Higgs boson's mass is so much lighter than what quantum corrections would predict. Given the vast energies associated with gravity, supersymmetry provides a mechanism where the superpartners cancel out these problematic corrections, naturally keeping the Higgs mass in check. More tantalizingly, the lightest supersymmetric particle, LSP, in many SUSY models is stable, weakly interacting and massive, making it an excellent candidate for dark matter. If SUSY is real, our universe is teeming with these invisible superpartners waiting to be discovered. Experiments at the Large Hadron Collider, LHC, have been diligently searching for signs of these particles, but so far they remain elusive, pushing the potential energy scale for their existence higher and higher. And this brings us back to the profound mysteries that the standard model simply cannot touch. Dark matter and dark energy. These aren't just minor footnotes. They are the dominant components of our universe. We observe their gravitational effects, galaxies spinning too fast to hold together with their visible matter alone, gravitational lensing bending light in ways that imply unseen mass, the accelerating expansion of the cosmos. Yet we cannot see them, we cannot directly detect them, and we do not know what they are. A true theory of everything must account for dark matter and dark energy. String theory, for instance, offers various ways to incorporate dark matter candidates through its extended particle spectrum, often involving weakly interacting massive particles, WIMPs, or axions. Dark energy, on the other hand, is even more enigmatic. Is it a constant energy density inherent to space itself, Einstein's cosmological constant, but with a value far smaller than predicted by quantum field theory? Or is it a dynamic, evolving field, dubbed quintessence? The answers to these questions lie beyond our current grasp, representing the ultimate frontier in our understanding of the cosmos. As we contemplate these grand theories, these magnificent attempts to unify everything, we sometimes encounter a philosophical idea known as the anthropic principle. This principle suggests that the fundamental constants of the universe, the strength of gravity, the mass of the electron, the precise value of dark energy, seem incredibly fine-tuned for the existence of life as we know it. If these constants were even slightly different, stars wouldn't form, atoms wouldn't hold together, or complex chemistry couldn't arise. The anthropic principle, in its weak form, simply states that we observe a universe compatible with our existence because, well, we exist. In its strong form, it suggests that the universe must have properties that allow observers to develop within it. This principle takes on a new dimension in the context of theories like string theory, which, due to its complex mathematical structure, may allow for an incredibly vast number of possible solutions, a quote 47 of different universes, each with its own set of physical laws and constants. If this concept is true, then perhaps we simply live in one of the universes where the conditions were just right for life to emerge. It's a profound thought, isn't it? One that takes us far beyond the equations and into the very nature of existence. Our journey through physics, then, is far from over. From the quiet emptiness of the atom to the majestic dance of galaxies, from the precise mechanics of the standard model to the speculative grandeur of a theory of everything, we are constantly pushing the boundaries of our comprehension. The questions that remain unanswered are not roadblocks, they are beacons, guiding us toward deeper truths, toward a more complete and harmonious understanding of the universe. The search for a grand unified theory, and ultimately a theory of everything, is not just about finding new particles or forces. It's about unveiling the profound unity that underlies all of reality, about discovering the elegant simplicity at the heart of the cosmos. It's a testament to the insatiable human curiosity, a quiet whisper in the vastness, urging us to keep exploring, to keep wondering, to keep reaching for the stars and the fundamental strings that might compose them. What astonishing revelations await us in the next chapter of this cosmic story? We can only continue our patient contemplation, our shared adventure, and prepare our minds for the wonders yet to unfold. We have journeyed far, haven't we? From the illusory solidity of our world to the bizarre dances of quarks and gluons, through the cosmic grandeur of space-time warped by gravity, and into the speculative realms of extra dimensions and supersymmetric partners. Our quest for a unified understanding for that elusive theory of everything has led us to the very edge of human knowledge, where the known gives way to the profoundly mysterious. But now, as we stand at this precipice, let us pause and ask a question that might seem almost too simple. Yet it holds the key to unlocking even deeper layers of reality. How do we know any of this? How do we, as observers, interact with the universe to extract its secrets. And what does that interaction, that act of observation itself, imply about the nature of reality? Up until now, we've largely discussed the universe as an objective entity, existing independently of us, waiting to be discovered. This is the classical view, the world of Newton and even Einstein's general relativity, a magnificent clockwork mechanism, operating according to precise deterministic laws, whether we are watching it or not. In this classical framework, our role as observers is passive. We simply measure what is. The moon, we'd say, is there even when no one looks. But then, the quantum realm entered the stage, shattering this comfortable picture. Remember our earlier encounters with the quantum world, the inherent fuzziness, the probabilistic nature, the particle-wave duality. These weren't mere oddities. They hinted at something far more profound about reality itself. Here, at the smallest scales, the act of observation, of measurement, isn't a passive act at all. It is, in a very real sense, an intervention. Consider again the electron, this elusive fundamental particle. Before we measure its position, where is it? Is it a tiny, definite speck somewhere, simply hidden from our view? Quantum mechanics tells us no. It is described by a probability cloud, a wave function spread out over space, representing all the possible places it could be. It exists, in a sense, in a state of superposition, simultaneously occupying multiple possibilities at once. It's like a ghost, everywhere and nowhere until you try to pin it down. And then we measure. We interact with it, perhaps by shining a photon at it, or by passing it through a detector. In that instant, something truly astonishing happens. The probability cloud. Quote 50. The electron, which was once a diffuse wave of possibilities, suddenly chooses a definite position. It materializes unequivocally at a single point. It's as if the act of looking forces it to make up its mind. This is the famous measurement problem in quantum mechanics, and it has haunted physicists for nearly a century. What constitutes a measurement? Does it require a conscious observer? Or is it simply any irreversible interaction with the environment? The implications are staggering. If reality is truly probabilistic until observed, if particles exist in a superposition of states until we probe them, does this mean that reality itself is not out there in a fixed, objective sense, but is instead intrinsically tied to our interaction with it? It's a dizzying thought, isn't it? It challenges our deepest intuitions about what quote 54 quote means. For centuries, philosophers and scientists alike have sought to understand the world as it is, independent of our minds. But the quantum revolution whispers a different story. Perhaps the universe doesn't just exist, it becomes through our engagement with it. This doesn't mean that the chair you might be sitting in ceases to exist when you close your eyes, nor does it imply that our thoughts alone conjure reality into being. That would be a misinterpretation. The quantum effects we are discussing are typically confined to the subatomic realm. Yet the principles are universal. They suggest that at the very bedrock of existence, there is an inherent indeterminacy that is only resolved through interaction. Some physicists grappling with this profound mystery have even begun to consider a radical idea that perhaps, quote 50 verbs, itself is a more fundamental building block of the universe than matter or energy. Imagine the universe not as a collection of particles, but as a vast, intricate network of information. Every interaction, every measurement, every particle's state, it all encodes and processes information. Think of it like this. When we say an electron has spin up or down, we are assigning it a piece of information. When it collapses from a superposition to a definite state, information is gained by the observer and the universe. The universe, in this view, is continually computing itself, constantly processing information. This perspective, sometimes encapsulated by John Wheeler's evocative phrase, quote, 58, quote, suggests that the physical world, quote, 59, quote, arises from fundamental units of information, quote, 60, quote. If information is truly fundamental, then the universe might be seen as a colossal information processing system. This isn't to say we live in a literal computer simulation, though that too is a fascinating and highly speculative idea that some brilliant minds have pondered. Rather, it's a way of looking at the universe's operational principles. It highlights how the very fabric of space-time, the interactions of forces, and the properties of particles could all be manifestations of underlying informational structures. This perspective also brings us back to the limitations of our perception. We, as human beings, are limited in our ability to perceive and process information. Our senses are tuned to a very narrow band of the electromagnetic spectrum. Our brains interpret reality through specific cognitive filters. What if there are vast oceans of information, entire dimensions of reality that remain utterly invisible and incomprehensible to us? Dark matter and dark energy, which constitute 95% of the universe's mass energy, stand as stark reminders of how much remains beyond our current grasp. Are they simply matter and energy we cannot detect, or are they manifestations of information structures we haven't yet learned to decipher? The universe, in its boundless complexity, often presents us with phenomena that defy our immediate understanding. The pursuit of physics, then, becomes a journey not just to categorize and explain, but to expand our very capacity for understanding. It's about stretching the imagination, developing new languages, like mathematics, to describe what our everyday senses cannot perceive, and building ever more sophisticated instruments to peer into the hidden depths. We seek not just to know what the universe is made of, but how it works at the deepest possible level. This includes looking for overarching principles, elegant symmetries, and conservation laws that govern all interactions. For instance, the very existence of fundamental forces and particles can be understood through principles of symmetry, a deep mathematical elegance that dictates how the universe must behave. When a symmetry is, quote, 61, quote, it can give rise to phenomena like mass, as is the case of the Higgs field. These principles are like the master strokes of a cosmic artist, guiding the intricate tapestry of existence. So, as we continue our adventure in the Dreamy Academy, let us embrace this profound dance between observer and observed, between the known and the unknowable. Let us appreciate that the quest for, quote, 62, quote, is not merely about accumulating facts, but about refining our very relationship with reality. It's about acknowledging the limits of our current understanding while relentlessly pushing those boundaries. The universe is not just a collection of particles and forces. It is a grand, unfolding narrative, and we, with our curiosity and our capacity for wonder, are an integral part of its storytelling. What deeper principles might lie beneath the surface, waiting to be revealed? What new insights will emerge when we truly grasp the informational underpinnings of reality? These are not questions with easy answers, but they are the questions that define the cutting edge of physics today. They invite us to contemplate, to dream, and to continue our patient exploration into the heart of existence. The journey continues always. If you've enjoyed this thoughtful exploration, please consider giving the video a like and subscribing to the Dreamy Academy. Your engagement fuels this shared discovery. Our journey through the fundamental nature of existence has led us to the precipice of what we know, and perhaps more importantly, what we don't know. We've peered into the quantum realm, wrestled with the enigma of observation, and contemplated the radical notion that information might be the universe's deepest currency. Yet, as we stand here, gazing out at the vast cosmos, an even more profound mystery looms, a shadow that encompasses the overwhelming majority of our universe, a reality that remains stubbornly hidden from our direct perception. Consider, if you will, the grand tapestry of the cosmos, woven with stars and galaxies, nebulae and planets. This is the universe we see, the universe of light, of electromagnetic interaction. But what if I told you that this visible universe, this dazzling display of cosmic fireworks, constitutes only a tiny fraction of what's truly out there? Indeed, all the stars, all the galaxies, all the dust and gas we can detect, everything that interacts with light, everything that forms the basis of our everyday experience and the standard model of particle physics, amounts to less than 5% of the universe's total mass-energy content. Think about that for a moment. 95% of the cosmos is shrouded in an impenetrable veil, existing as what we tentatively call dark matter and dark energy. What does it mean for our understanding of reality when almost all of it remains unseen, unmeasured, and profoundly unknown? It's like trying to understand a vast ocean by studying only the foam on its surface. We are truly navigating a sea of ignorance, guided by the faint gravitational ripples of these unseen behemoths. Let's first turn our attention to dark matter. We infer its existence not because we see it, but because we observe its gravitational pull. Galaxies spin faster than they should if they only contain the visible matter we detect. Galaxy clusters are held together by far more gravity than their luminous components can account for. Light from distant objects is bent and distorted as it passes through regions of space that contain far more mass than we can see, a phenomenon known as gravitational lensing. These cosmic discrepancies are the fingerprints of dark matter. It doesn't emit, absorb, or reflect light, or indeed any other form of electromagnetic radiation. It passes right through us, through the earth, through everything, like a silent, ghostly wind. We are swimming in a sea of it, yet we remain utterly oblivious to its presence, save for its gravitational embrace. What is it? The leading candidates are exotic, yet undiscovered particles that fall outside the standard model. Perhaps WIMPs, weakly interacting massive particles, which would be many times heavier than a proton, interacting only through gravity and the weak nuclear force. Or maybe axions, incredibly light particles proposed to solve a different problem in quantum chromodynamics, but which could also contribute to the dark matter density. Despite decades of painstaking experiments, deep underground in shielded laboratories, trying to catch a dark matter particle in the act of a rare collision, we have yet to find direct evidence, it remains one of the universe's most tantalizing riddles, a constant reminder of the limits of our current particle physics framework. Then there is dark energy, an even more enigmatic entity, constituting an astonishing 70% of the universe. If dark matter acts like an invisible gravitational glue, holding galaxies together, dark energy behaves like a cosmic anti-gravity, pushing the universe apart at an ever-accelerating rate. For billions of years after the Big Bang, gravity was the dominant force slowing the universe's expansion. But about 5 billion years ago, something shifted. The expansion began to speed up, and it continues to accelerate today. This acceleration cannot be explained by any known form of matter or energy. The simplest explanation for dark energy is a cosmological constant, a term introduced by Einstein into his equations of general relativity, only to later dismiss it as his biggest blunder. Ironically, it seems he might have been right all along. This constant could represent the inherent energy of empty space itself, a vacuum energy. But if we try to calculate the expected energy density of the vacuum based on quantum mechanics, the result is an astronomical number, many orders of magnitude larger than what observations suggest. This discrepancy is arguably the worst prediction in the history of physics, a profound clash between our two most successful theories. Alternatively, dark energy could be a dynamic, evolving field, dubbed quintessence, that permeates space-time, its properties changing over cosmic time. This would be a new fundamental force or particle, something entirely unexpected. But for now, dark energy remains a placeholder for our ignorance, a label for the phenomenon of accelerated expansion, without truly understanding its underlying nature. It challenges our understanding of gravity, of space-time, and of the very fabric of existence. These two dark components, dark matter and dark energy, are not mere footnotes, they are the main story. They are the scaffolding upon which the visible universe hangs, yet they remain stubbornly beyond our grasp. They scream for a physicist beyond the standard model, for a deeper, more comprehensive understanding of the cosmos. This brings us back to the grand quest, the search for a theory of everything, TOE. Remember the grand schism between general relativity, describing the smooth curved space-time of gravity on cosmic scales, and quantum mechanics, depicting the grainy probabilistic reality of the very small. Dark matter and dark energy only amplify the urgency of bridging this divide. A true TOE would not only unify all four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, into a single, elegant framework, but it would also shed light on these dark mysteries. It would explain the fundamental parameters of our universe, the masses of particles, the strengths of forces, and perhaps even why there are 3 generations of matter. Imagine a single equation, a singular concept that could describe everything from the dance of quarks within a proton to the majestic swirl of galaxies across billions of light years. Such a theory would necessarily incorporate quantum gravity, resolving the paradoxes of black holes and the Big Bang, where both general relativity and quantum mechanics must operate at their extremes. It would tell us what space-time truly is at its most fundamental level. Is it a continuous fabric, or is it woven from discrete threads, like the loops in loop quantum gravity? Or perhaps it arises from the vibrations of tiny multidimensional strings, as proposed by string theory and its more encompassing successor, M-theory. In the realm of string theory, particles are not point-like entities but rather minuscule, vibrating strings, each distinct vibration corresponding to a different particle. Gravity, in this view, is simply one of these vibrational modes, a spin 2 particle called the graviton. This elegant framework intrinsically includes gravity and offers the tantalizing prospect of unifying all forces. But string theory typically requires extra spatial dimensions. Dimensions curled up so tightly that we cannot perceive them, like a garden hose appearing as a line from afar but revealing its circular dimension up close. Could our reality be a mere brain floating within a higher dimensional bulk? Such ideas stretch the imagination to its limits, but they offer potential pathways to understanding why gravity is so much weaker than the other forces, or even how dark matter might manifest as particles from these hidden dimensions. Loop quantum gravity, on the other hand, rejects the notion of extra dimensions and instead proposes that space-time itself is quantized, made of discrete loops or atoms of space, a network of interwoven quantum threads that give rise to the smooth space-time we perceive at larger scales. In this view, space is not an empty stage upon which events unfold, but a dynamic, granular entity, constantly fluctuating at the Planck scale, the smallest conceivable length where quantum gravity effects would become dominant. These are not just mathematical exercises, they are profound philosophical inquiries into the very nature of existence. If string theory is correct, then the universe is a symphony of vibrating strings, and reality is a multi-dimensional dance. If loop quantum gravity holds true, then space and time are not fundamental but emergent, woven from an intricate quantum fabric. Both offer radically different pictures of fundamental reality, and both seek to encompass the mysteries of dark matter and dark energy within their frameworks, albeit in different ways. The quest for a TOE is a testament to humanity's insatiable curiosity, our deep-seated need to understand our place in the cosmos and the underlying order of the universe. It's a journey that demands patient contemplation, an open mind, and a willingness to confront the limits of our perception. We are not just seeking equations, we are seeking a deeper truth about what it means to be, what it means for anything to exist. As we continue to explore these grand, unifying theories, we are also forced to confront the role of information and observation on an even more cosmic scale. If dark matter and dark energy are truly fundamental aspects of the universe, yet we cannot directly observe them, what does that say about the completeness of our quote 70 of reality? Are we missing entire chapters of the cosmic story because our senses and instruments are simply not tuned to their frequencies? The universe, it seems, is far richer and more complex than our everyday experiences suggest. The visible world, the world of matter and light, is but a fleeting glimpse into a much grander, largely unseen reality. Our current theories are like magnificent lighthouses, illuminating vast stretches of the scientific ocean, yet leaving immense, mysterious waters still uncharted. The journey, dear friends, is far from over. In fact, in many ways, it feels as if it has only just begun. And as we venture deeper, remember to keep that sense of wonder alive, for it is the fuel that propels all true discovery. We left our last shared contemplation adrift in a sea of unknowns, didn't we? The universe, as we understand it, is overwhelmingly composed of dark matter and dark energy, invisible architects shaping a cosmos we can barely perceive, let alone comprehend. These enigmatic components, silent and elusive, stand as towering monuments to the limits of our current theories, beckoning us towards a deeper, more profound understanding. They remind us that the standard model, for all its triumphs, is but a partial map of an infinitely vaster territory. But even as we grapple with these colossal mysteries, another equally astounding puzzle presents itself. It's a puzzle not of what we can't see, but of what we can. Look around you, at the solidity of your chair, the light filtering through a window, the gentle hum of existence. All of this, everything you perceive, every atom in your body, every star in the night sky, hinges upon a breathtakingly precise set of cosmic parameters. Imagine a grand universal control panel, adorned with an impossibly intricate array of dials and sliders. Each dial represents a fundamental constant of nature, the strength of gravity, the electromagnetic force, the weak and strong nuclear forces, the masses of elementary particles, the very energy density of the vacuum of space. Now, imagine that these dials, by some unfathomable cosmic lottery, have been set to values that are not just favourable for life, but exquisitely, almost impossibly, perfect. Consider, for instance, the strength of the strong nuclear force. If it were just a few percent weaker, atomic nuclei wouldn't hold together, and no elements heavier than hydrogen could ever form. No carbon, no oxygen, no iron, no building blocks for stars, planets, or life itself. Conversely, if the strong force was slightly stronger, hydrogen would fuse too readily, consuming all the universe's fuel before complex structures could emerge. Stars would burn out in a flash, and the universe would be a sterile, short-lived inferno. Or think about the electromagnetic force. Its delicate balance with the strong force allows electrons to orbit nuclei, forming stable atoms. Alter it even slightly, and either electrons would escape their atomic prisons, or they would collapse into the nucleus, leaving a universe devoid of chemistry, devoid of light. And then there is the cosmological constant, that elusive quantity linked to dark energy, which determines the expansion rate of the universe. If it were significantly larger, the universe would have expanded so rapidly that matter would never have coalesced into galaxies, stars, or planets. A universe of thinly dispersed dust, forever expanding into cold oblivion. If it were slightly smaller, the universe might have collapsed back in on itself long before life had a chance to bloom. The observed value of this constant is so extraordinarily tiny, so perfectly tuned, that it beggars belief. It is like hitting a target the size of a pea in a football stadium from a distance of billions of light years, blindfolded. This remarkable precision, this apparent fine-tuning of the universe, the emergence of complexity and consciousness, poses one of the most profound questions in all of physics. Is this just an astonishing coincidence, or is there something deeper at play? This is where the anthropic principle enters our quiet contemplation. It's not a physical law in the traditional sense, but rather a philosophical argument, a way of framing the question. The weak anthropic principle simply states that the universe must be compatible with the existence of intelligent observers, because we are here to observe it. It's a selection effect. We can only find ourselves in a universe where the conditions allow for our existence. It's like observing that all fish live in water. It's not surprising given that fish cannot live elsewhere. But the strong anthropic principle goes further, suggesting that the universe must have properties that allow for life to develop at some stage. This version often feels less like science and more like teleology, implying a purpose or design. It raises more questions than it answers, nudging us towards the realm of metaphysics. Neither version truly explains why the constants have the values they do. They merely acknowledge the observation. So, if it's not just a cosmic coincidence, and the anthropic principle isn't a fundamental explanation, what else could account for this exquisite fine-tuning? This is where our imaginations must truly stretch, where we venture into the grand, speculative landscape of the multiverse. What if our universe isn't the only one? What if, instead of a single cosmic lottery ticket being drawn against impossible odds, there are an infinite number of tickets, an infinite number of universes, each with slightly different fundamental constants, different laws, different initial conditions? In such a scenario, the apparent fine-tuning of our universe becomes less miraculous. If every possible combination of physical constants is realized in some corner of an infinitely vast multiverse, then it stands to reason that at least one of these universes would possess the exact properties necessary for stars to ignite, elements to forge, and life to blossom. We, as observers, would naturally find ourselves in one of these rare, hospitable universes, because we couldn't exist anywhere else. It's the ultimate selection effect, writ large across the fabric of existence. Where do such multiverse ideas come from? They emerge from some of our most promising theoretical frameworks, notably string theory and thus inflationary cosmology. Recall our discussion of string theory, where fundamental particles are not points but tiny vibrating strings. The way these strings vibrate, and how the extra dimensions of string theory are, quote, 72, quote, or curled up, determines the specific physical laws and constants we observe. String theory predicts a vast number, perhaps as many as 10 to the power of 500, of possible ways for these extra dimensions to compactify, each corresponding to a different set of physical laws and constants. This immense collection of possibilities is often referred to as the, quote, 73. Each point on this landscape represents a distinct universe, a different, quote, 74 with its own unique properties. Our universe, then, would simply be one particular valley in this unimaginably vast landscape, a valley whose specific contours happen to be perfect for life. Another compelling origin for the multiverse lies in the theory of eternal inflation. Inflation, as you might remember, is the rapid exponential expansion of the early universe, which smoothed out anisotropies and solved several cosmological puzzles. But what if inflation, once it starts, doesn't stop everywhere? What if, in some regions, it continues indefinitely, constantly spawning new bubble universes that pinch off and expand, each with potentially different physical laws? Imagine an endlessly frothing cosmic ocean, where each foam bubble is a nascent universe, inflating and evolving independently. Our universe would be just one such bubble, a momentary pocket of stability within an eternal, chaotic process of creation. The implications of a multiverse are profound. It shifts our perspective from a potentially unique, specially designed cosmos to one of an ensemble, a statistical outcome. It means that the laws of physics we cherish might not be universally constant across all of existence, but rather local manifestations of a grander, more flexible meta-law. It suggests that our quest for a theory of everything might not just be about unifying the forces within our universe, but about understanding the overarching framework that allows for the creation of countless universes, each with its own everything. This idea, while exhilarating, also presents immense challenges. How could we ever detect another universe? How could we verify such a hypothesis? For now, the multiverse remains largely in the realm of theoretical speculation, a powerful conceptual tool for addressing the fine-tuning problem, but one that pushes the boundaries of empirical science. Yet, the very fact that our most advanced theories point towards such possibilities is a testament to the audacious reach of human thought. As we ponder these grand vistas, we return once more to the notion of information. If the universe is a tapestry woven from information, as we mused in Chapter 7, what then is the information of the multiverse? Is there a meta-information, an overarching code that defines the parameters of all possible universes? Could the entire cosmic ensemble be seen as an ongoing, infinitely complex computation, exploring every possible permutation of physical laws? Such questions verge on the philosophical, perhaps even the spiritual, but they arise naturally when we push the boundaries of our scientific understanding. Our journey through physics, from the quiet emptiness of matter to the dark, expansive mysteries of the cosmos, has been a testament to the incredible power of human curiosity. We have built models of reality, tested them with astounding precision, and yet, at every turn, we encounter new depths of wonder and new frontiers of ignorance. The fine-tuning problem, the dark universe, the clash between quantum mechanics and general relativity, these are not failures of physics, but rather invitations. Invitations to delve deeper, to question more profoundly, to imagine more boldly. The universe, in its infinite wisdom, does not yield its secrets easily. It demands patience, perseverance, and a willingness to embrace the unknown. It asks us to confront the limits of our perception, to acknowledge the vastness that lies beyond our immediate grasp. But in this ongoing struggle, in this shared quest for knowledge, we find not frustration, but exhilaration. For every answered question reveals a dozen more, each more captivating than the last. So, as we bring this particular contemplation to a gentle close, let us not be daunted by the enormity of what we do not yet know. Instead, let us be inspired. Let us carry forward the spirit of inquiry, the quiet wonder, and the profound appreciation for the elegance and mystery of existence. The journey of physics is far from over. It is an eternal exploration, a continuous unfolding of reality, and we, dear friends, are privileged to be a part of it. Keep observing, keep questioning, keep dreaming, for in the heart of every mystery lies the seed of a new discovery, waiting to illuminate the path forward. And perhaps, just perhaps, the universe is even stranger, more beautiful, and more interconnected than we can possibly imagine. Thank you for joining me on this slow and thoughtful adventure through the heart of physics. If you found this journey illuminating, do remember to like the video and subscribe to the Dreamy Academy for more shared explorations into the profound truths of our universe. Until next time, keep your mind open and your gaze fixed on the stars. They hold more secrets than we can ever hope to count.